So next, let's try and solve, let's go back to a first order. Let's try and solve y prime is, let's say 4xy. Okay, so y prime is 4xy. Again, power series are a terrible way to do this. This is a separable differential equation. It's first order linear. Mainly it's separable. I think separable is the easiest way here. So we'll see what our answer should be in a second. But what we're going to do is we're going to write the power series representation, figure out what happens here. The reason why I wanted to do this is that we have this x term, and that's going to be slightly annoying here. So this is going to be c sub n x to the n. We're going to sum from n equals 0 to infinity. Our y prime, just like always, is going to be the sum starting at 1 of n c sub n x to the n minus 1. And then we're going to set these two terms equal. So we're going to take the representations for y prime and y and plug them into our differential equation. So our differential equation is going to become the sum starting at 1 to infinity n c sub n x to the n minus 1 is going to be equal to 4x times y. So this is the sum starting at 0, n equals 0 to infinity c sub n x to the n. Okay. Now, we're going to have a difficulty here if you can't see it already. So the first thing that we're going to be allowed to do, the first thing, is we're going to take this 4x on the right side and push it inside the sum. Don't mess with the left sum quite yet. So this is going to be the sum of, as n goes from 0 to infinity. The 4x can move inside because 4x is a constant with respect to the variable of our index. It's the index of our sum, n. So we're summing in n. That means that x is a constant with respect to n. We can move it inside and everything is fine. So you have 4 c sub n. And then if you multiply x by x to the n, you get x to the n plus 1. Okay, and we're going to have a slight problem here. There's going to be two ways that we can handle this, but the slight problem that we're going to have is that now there's a slight discrepancy here. The sum on the left starts with a constant term, because when n is 1, you're going to end up with 1 c1 times 1. Okay, so this left sum is c1. Let's just look at the first few terms. When n is 2, you're going to get 2c2 times x, 3c3 x squared, 4c4 x cubed, and so on. Okay, that's this left side. The right side is going to be, let's just think about what are the first few terms that we're going to have. When n is 0, we're going to have 4c0 times x. So that's already a difference from before. There is no constant term on the right side. The first term is a linear term. We'll have 4c1 times x squared, 4c2 x cubed, and 4c3 x to the fourth, and so on. Okay, and so what we're going to do, and there's really two methods here, but I want to explain both of them. You can take this expression, and you can just, since these are two power series representations, the way I've written it here, these are still two power series that we're equating. They're equal. So you can take and compare the terms. So it turns out that you get C1, you get C1 is 0 because there is no constant term on the right side. So you could think of that term as 0. So C1 is 0. 2C2, we're going to equate to this linear term here. That's going to be 4 C0 times x. I'm sorry, no x. I'm just equating the constants here. And then 3C3 is going to be equal to 4C1. So 3C3 is 4C1, and so on. 4C4 is going to be equal to 4c2. And then we could figure out what's going to happen from here. We're going to need a constant again. So let's call C naught, let's call that A. And so C1 is going to be 0. C3, well, C2 is going to be 2A. C3 is going to be 4/3 times C1, but that's just 0. C4 is going to be the same as C2, so that's 2A. C5 will be, so 5C5 is going to be equal to 4C3. And 6C6 is 4C4. So that means that C6 is going to be 2/3 of C4. So that's 4/3 A. And the pattern's pretty hard to spot. That's why I like to not simplify everything. So that's the first way, and you can kind of figure out what the terms are going to be that way. And that's kind of a measure of last resort. So if you can't think of anything else to do, you can just write out the power series, equate all the like terms. So what I mean by that is that you equate the constant terms, you equate the linear terms, you equate the quadratic terms, and so on. Right? So all the corresponding powers must have matching coefficients if the two power series are equal. Now, one other way that we could do this is let's go back and let's look at this sum. So I'm going to rewrite this sum. This is the sum starting at n equals 1. So this is just an alternative method. So we have the sum starting at n equals 1 to infinity, n c sub n x to the n minus 1. That's going to be equal to the sum n equals 0 to infinity 4 c sub n x to the n plus 1. Okay, so this is the expression that we're going to have to contend with here. Now, again, notice that the first term here is going to be a linear term. So what we're going to do is I'm going to replace our n with n plus 2 so that we get matching powers. Okay, so this is going to be the sum. Let's think about the best way to describe this. Actually, the first thing I'm going to do is, just so that everything works out nicely, I'm going to peel off the first term on the left side. What I mean by that is that when n is equal to 1, what we get is 1c1 times x to the 0. And then if I take out the n equals 1 term, what we're left with is all the terms from n equals 2 to infinity of the same expression. Okay. And again, the reason why I just took off 1 term is that we know that these sequences are just off by 1. So this left sequence starts with a constant, the right sequence starts with a linear expression. Now I'm going to replace n with n plus 2. So don't worry about C1. If I replace n with n plus 2, we're going to get n plus 2, c sub n plus 2, x to the n plus 1. And that's going to be equal to this sum over here. So from n equals 0 to infinity, 4cn x to the n plus 1. And now everything is fine. Now we have power series representations that are equal. We have power series that have the same power of x. They have the same starting index, so we can just equate them with one another. Notice that there's no constant on the right side, so if you want, you can imagine that there's a 0, but this tells you that C1 is 0. And then, like always, we're going to assume that the first value, because it's a first order differential equation, right? We are solving y prime equals 6xy. Because it's a first order differential equation, we just have one constant. So C0 is A, C1 is 0, and then here we know that n plus 2 times c sub n plus 2 is going to be equal to 4 times c sub n, and this is going to be for all n greater than or equal to 0. And so this tells you that c sub n plus 2 is going to be 4 c sub n over n plus 2. And so from this, you can get that we can just find the next value. So C2 is going to be that's when n is 0. So you're going to get 4 C0 over 2. C3 is going to be some constant times C1. C4 is going to be 4 times C4 over 4. So that's going to be, let's see, C4 was 4 times, I'm sorry, this is 4 times C2 over 4. So C2 was 4 times C0 over 2. So this is 4 squared times C0 over 4 times 2. C5 is going to be a multiple of C3. And in fact, all the odd terms are going to go away. C6 is going to be 4 times C4 over 6. So that's going to be 4 cubed times C0 over 6 times 4 times 2. And in general, what's going to happen, if you notice the pattern, is that the odd terms are 0 for all n, and the even terms are going to be, just notice that what can happen here is you have 4 cubed over C0, and notice that each of the terms in the denominator kind of looks like a factorial, except not quite. But if you factor a 2 out of each of these, you can factor a 2 and a 2 and a 2, and that'll give you 2 cubed. And what you're left with is 3 times 2 times 1. So this is going to be 4 cubed over 2 cubed is 2 cubed. C0 over 3 factorial. And in general, C sub 2n, the even terms, are going to be 2 to the n, because what you do is you take your subscript and divide by 2, so that's your power. So C6 had 2 cubed, so that's 6 over 2. Times C0, which is our a. I don't know why I'm not writing a instead of C0, but all the C0s here should be a, divided by n factorial. So this is 2 to the n times a over n factorial. And now we're going to take our power series representation. We're going to have to do the even and odd trick like we did before. So our power series C sub n x to the n as n goes from 0 to infinity will split into the even and the odd terms. So C sub 2n x to the 2n plus C sub, that scribble should have been a 2n plus 1, x to the 2n plus 1. N goes from 0 to infinity. And then notice that the odd terms are all 0, because that's what we found for our expression here. These odd terms are all 0. So actually, this is just going to be 0 for this term here. The only time, I do have to say, and I just want to take a step back here, the only time when the sequence is 0, but you still have something in your function, is when you have 0 to the 0. So I'll put a pin in that and come back in that for just a second. But let's finish this. So C sub 2n, we said is 2 to the n times a over n factorial. So that's our C sub 2n, x to the 2n. Okay, and then this is the sum starting at 0 to infinity. The other sum is a big old 0. And so this is going to be, let's bring out the a. 2 to the n in x to the 2n is going to be 2x squared to the n all over n factorial. And again, this looks like an exponential function, and it is. This is a times e to the 2x squared. Okay, so this tells you that your solution to this differential equation is a constant times e to the 2x squared. And that makes good sense, because when you differentiate this function, you're going to get the same function that you had times 4x, right? That was the equation that we were solving. Right, so this really does satisfy y prime equals 4xy.